Hi, I'm here with Brian Beckman. He's a research engineer at Meta Reality Labs, and I'm here to interview him about his job.
All right.
So, what was your major, and tell me a bit about your current job?
Oh gosh. Okay. My major was physics. My PhD is in astrophysics,
Oh, okay.
and my current job is working on smart glasses. So, as in my generation of physicists, if you wanted to do computing, you wrote your software, all of it, from the operating system to the compilers, the debuggers. You wrote everything. There wasn't much available. So the very first time I got any software handed to me was in the late 70s when Unix and the original Kernahan-Ritchie C compiler came out. And then we didn't have to write everything ourselves anymore. But I had done a lot of that before. Part of my PhD work was image processing on extremely deep plates of the Coma cluster. Coma cluster of galaxies is about 600 million light years away, I think, if I remember correctly. And it's one of the biggest and heaviest objects in the entire universe. It's extremely interesting to study for the dark matter problem. So to study the dark matter problem, you need to know two things. How much dark? Well, you can't measure dark, so how much light, and dark is the opposite of light, and how much matter. Matter you can measure by measuring the velocities. So the more matter there is, the faster things spin around. And you can measure velocities by redshifts and blue shifts. So if you got a disk and they're coming toward you, they're blue shifted. If they're going away from you, they're red shifted. You can tell how fast they're going. And then you measure, that measures the mass, and then you measure the light, which is what I did for my work. And we wrote a whole bunch of software to do that on various kinds of computers. So I learned how to do embedded systems early in my life just so I could do, do my physics work. And then later, so that's what we're doing with the glasses. So this is like coming around, like 50 years later, here I am working on embedded systems again. It's lots of fun. I have lots of experience doing it.
So what does like a typical day on your current job look like?
Very good question. Usually the first thing I try to do is drain my email inbox, because if I forget to do that, it will pile up and it'll be a big mess. Most of what's in there are notices for me to review other people's code. So the way Meta works, and most big companies do, is code has to be at least read by another engineer. And it's universal. You can have the very best engineer in the world and he writes code and somebody's got to read it. I will do 5 or 6 code reviews in the morning before I get started. Then we organize our work around tasks. Tasks are just a description of what you need to do. Sometimes they're very rigid, like you got to do it, there's a deadline, and sometimes there isn't. It's a great system because otherwise you go completely crazy multitasking. So I have my work life organized into a Google Chrome window full of code, another one full of tasks, another one full of docs, and another one full of wikis. Those are the main things that we use to communicate with one another. And if I didn't do that, I would seriously go insane. I'd have 400 open tabs. As it is, I've got many, many, many open tabs and things that are kind of like partway through. Some days I'll spend coding. Some days I'll spend going to meetings, and some days I will spend writing docs and wikis.
And do you like find yourself doing like the same-ish things each day, or does it change up a good bit?
It changes up a good bit. The current system we're working on is pretty complicated, and so most of the time we're just trying to integrate pieces together, and there can be a lot of different, combinatorial number of interesting issues that nobody thought of when they wrote the code.
Yeah.
Then we try to put it together. Concurrency is the most interesting kind of issue. That's where you have multiple threads of execution going on at the same time, sometimes on the same device, multi-threads on the same device, sometimes code running on one device and code running on another device, and they have to coordinate. And there are many, many ways that can go haywire.
Yeah. And what would you say is your favorite part about your job?
Favorite part about my job here at Meta is the people. The people here are super cool. It was very surprising to me. I did not expect Meta to be such an open and endearing culture, but it is. Everybody is willing to help. You know, when you come in, I'll just speak of my own experience. Coming into a mature project with 10 million lines of code and trying to do some engineering you feel like you're drowning right away. And if you don't get help, you don't learn anything. And people here are incredibly generous with their time and help. And I'll ask the stupidest questions, like, how do I build this module? Well, what they could say is, you idiot, read the doc. Well, which doc? There are 400 docs, right? So they don't do that. They'll point you to the right thing and get you going right away. And it just takes time to learn a big, complicated system like this. And these people make it pleasant instead of horrific.
No. And if you had to say, what would be your least favorite part about your job?
Least favorite part? That's a good question. When breakfast is over, I'm sad. And when lunch is over, I'm sad. No, actually, the least favorite part of the job is commuting home in the afternoon. I come in at 6 in the morning and I try to get out by 3 because any later than that, and it takes me an hour to go 12 miles home.
Ooh.
Yeah, so I live in kind of a non-optimal pattern of the flow velocity of the traffic here. Yeah.
And how do you get into this field? Did you have a job before this?
Oh my God. So you're asking me to encapsulate 50 years. So I gave you a hint at the beginning. I learned how to write code on all kinds of computers to do anything at a very young age. The next most interesting project I worked on many years ago, this is in the early 80s, was very long baseline interferometry. So this is, you got, I worked at Jet Propulsion Lab. So let me just, in case we run out of time, I'll give you the quick history.
Okay.
Jet Propulsion Lab for 10 years.
Like straight out of college?
Yeah.
Okay.
Microsoft for 20 years. Amazon for 8 years. A little tiny chip company for 4 years. And here for about 4 months.
Okay.
So and then before that, I got my PhD at Princeton, and I was very deeply attached to Bell Labs. Right next door to Princeton, and I was working for Arno Penzias, who has the Nobel Prize for discovering the cosmic microwave background, and there were 3 Nobel laureates on my doctoral oral committee. So it was that was really great. I count those, even though I was only paid a graduate student stipend, I count those as work years because I learned a lot there. But at Jet Propulsion Lab, very long baseline interferometry. JPL owns a network of radio telescopes. It's now called Descanso. It used to be called the Deep Space Network. These are 200-foot dishes.
Oh.
There are at least 12 of them in the world, and they're used for spacecraft navigation. But they can also be used for interferometry. What is interferometry? You've got some noise coming into one telescope. You've got the same noise coming into another telescope. And if you can measure the time delay, then you can, do trigonometry to figure out where stuff is. What good is that? Well, you need to figure out where the telescopes are. Why do you need to figure out where the telescopes are? So you can figure out where the spacecraft is.
Yeah.
Interferometry, by the way, just means beating those signals against each other. So you may remember from signal processing that if you beat signals against each other, you get much higher resolution because you do the sum and the difference of every Fourier component. So let's see. The coolest thing about that is we could directly measure tectonic drift.
Oh.
You have
okay.
one telescope in Hawaii, you have another telescope in Massachusetts. We know historically by looking at the trajectory of the Emperor Seamount chain that it's about an inch a year.
Okay.
But with interferometry, you can directly measure it.
Yeah.
It's because you can get sub-millimeter precision
Oh.
on these waves, on these radio signals. In order to do this, we needed a big parallel computer. It was called a correlator because we're correlating the signal, right? So that now I had learned just, ordinary computing in graduate school, and I learned distributed concurrent computing and distributed concurrent parallel computing to work on the correlator. And then the next thing I did at Jet Propulsion Lab is called the time warp operating system. The time warp operating, have you heard of a page fault in an ordinary operating system?
I have not.
Have you heard of virtual memory?
No.
So you may know that when you write a program, you have an imaginary address space that is much larger than the memory that you have in the computer.
Yeah.
Like it's 64 bits. No computer will ever have 2 to the 64 bytes memory. So what does it mean when you reference an address in your program and that address is not actually in the physical memory? The operating system does some magic behind your back. What it does is it's called paging. It will take data from the disk and put it in memory at the pretend addresses that you are, okay? So it's called virtual memory. It's a whole subject by itself. If you get into writing very efficient programs, you don't want to use virtual memory. You want to avoid virtual memory because this page swapping is expensive.
Yeah.
Or at least you want to engineer around it. Not around it, but engineer it so that you do your page swapping in a smart way. What we did with time warp was time faults.
Okay.
So you have your memory is arranged in space this way. It's also arranged in time that way. What does that mean? That means your program is executing these addresses now, and it's executing other addresses later. And so we can do a time fault. That means if you get instructions that are in your virtual past, you restore a saved state and compute forward again with the correction. So, let's say you get some instructions that say launch the missiles, and then later on some message got delayed and it said don't launch the missiles.
Yeah.
So you can actually unlaunch them in this operating system because we saved the pre-launch state and we restore the state. So I wrote the whole not every layer of it, but the primary executive layer for that operating system, and that was a great success. Because of that, Microsoft, an operating system company, recruited me. I went to Microsoft and I did many things. It's easier to say what I didn't do in 20 years. I never worked on Office.
Okay.
And I never worked on GUIs.
Yeah.
I worked in Windows kernel. I worked in Microsoft Research. I was the number 6 hire in Microsoft Research. I worked in programming languages and just everything. After that, I went to Amazon. I officially retired from Microsoft. And then my friend called me up. Every job I've ever gotten is somebody calls me up and says, hey, come work for me. And that happened here too with Misha. People remember me and they like working with me and they call me up and they offer me a job for free. I got to come in and interview and qualify and stuff like that. But I don't normally apply for jobs. It's just people who remember me. So my boss from Microsoft had left Microsoft, gone to Amazon, heard I retired and called me up and said, hey, come along, I need you. So what I did at Amazon was mostly what's called back-end systems. Amazon has, you can imagine with thousands of sales per second.
Yeah.
They have a big back end to manage this business flow. And one of the problems was that there was a delay between a product going bad and Amazon's finding out about it. So an example is you may have some product that got a bad batch and the return rate on it goes up. So I'm not telling you what this is, but it's a real story, and it cost the company a lot of money because they didn't find out for 2 days. And the reason they didn't find out for 2 days is they were storing this data in a data warehouse, and that's slow. There's just a delay, and there's systems pounding on it thousands of times a second. So what I built for them was a system that catches these streams of bad product reports and reports them within seconds instead of days. It saves the company a lot of money because you find out right away something's going wrong. And so that was a big deal. And then a few of us founded Prime Air, the drone delivery project. V1 of the drone delivery project is never shipped. They're in V2 now, and they're doing it with a new crew that is doing it the traditional aerospace way. We were trying some things that maybe were a little adventurous.
Okay. And then that brought you to Meta?
After that, I met somebody there who was working on a very exciting idea in chips.
Oh, right, yeah.
The chips that they're working on, this is GSI technology. The chips are very wide SIMD machines.
Oh, okay.
So I joined the company when I saw them do 128,000 16-bit ads in 12 clocks. I thought, that's cool. Yeah. Maybe we can do something with this. So I wrote some compilers and assemblers for them, and that work, they ended up deciding they couldn't afford to fund a full compiler group. Normally when you create chips, you create the compiler along with it. It's called co-development, and you need a big crew to do that. Especially, we wrote great prototypes, but competing against the likes of NVIDIA and Microsoft and so on, you have to have a big compiler group. So they decided they'd had enough of that, and they went back to just working on their hardware, and maybe they someday will want to revive it. Our work survives as LPython on GitHub. So we open sourced the backbone of that product. It's freely available for anyone, and it is a Python compiler. It doesn't compile all of Python. Python is not really compilable. It's an inherently dynamic programming language. The portion of Python that it does compile, our guarantee is it will never be slower than C. Okay. This is really cool because one of the main complaints about Python is it's slow, because it's an interpreter. It's interpreted, and there's not native parallelism inside the language and stuff like that. So we took a portion of Python and we're working very, very hard to make it fast.
And then how do you get into all this stuff? Was there a moment that you knew you wanted to do this?
I guess what you would call me is a generalist.
Okay.
I'm generally interested in all kinds of things.
Got it.
So I've done science, I've done mathematics, I've done programming languages, I've done operating systems, and I'm like a little kid. You say, this sounds cool. Okay, let's do it.
Yeah.
So it's my life has been a little bit of a random walk, but I don't mind, and people who put me to work, they don't mind, and so everything's okay.
Right. And would you have any parting advice for someone pursuing a career in STEM generally?
That's a great question. There's so many different kinds of people that it's really hard to give generic advice. If I had to give it generic advice, it would be pay attention to the mathematics.
Okay.
Develop a habit for first principles. Don't take things for granted. If something doesn't look right to you or doesn't feel right, your intuition is telling you there may be something wrong, and go ahead and dig into it. So and maybe to a fault, I'm a first principles guy. I don't believe it if I can't re-derive it myself from first principles. Sometimes that's not practical and you have to take things on faith. And actually, a lot of the time, software testing stands in for mathematics. If I can write enough good tests, then I'll trust something. But that would be my my main advice. I don't mean unless you want to be a mathematician.
Yeah.
You don't need to go whole hog on exotic mathematical subjects. But get the fundamentals down. Pay attention to linear algebra. Really, differential equations, and the new stuff is differential geometry. Everything is going this way. Lie groups and differential geometry on Lie groups. This is ways to exploit symmetry for solving equations. Really, I think every young person needs to learn it. I didn't learn it coming up because it wasn't a big topic. We did everything the old-fashioned way with tensors and IJK, LM indices, and that kind of stuff. But it's not done that way anymore, and I think it's a good thing that it's not done that way anymore.
Yeah.
But if you don't get it taught in school, learn it on your own.
Okay. Well, thank you very much for your time.
You're welcome.